All right, today we're tackling a concept that is just on a truly monumental scale. I'm talking about designing a beacon, one that could be seen across entire galaxies. And no, this isn't just a fun sci-fi thought experiment. We're gonna dive deep into the real physics and the hard engineering behind what it would take to build an interstellar lighthouse, a megastructure that could last for, well, eons.
So, here's the big question, the one that kicks this whole idea off. How could a civilization build a beacon that could literally outshine a galaxy without actually powering it themselves? I mean, forget about building some colossal power station and beaming energy into space. What if instead you could just hijack one of the most powerful things in the entire universe and, just tweak its signal? This is a totally different way of thinking about SETI, the search for extraterrestrial intelligence.
So let's break that down. You've got two main approaches here. On one side, you have active beacons. This is what we usually think of, building a massive transmitter and just blasting radio or laser signals out into the void. It's like shouting into the cosmos. The big problem? It takes a ridiculous amount of power, constantly. But then you have this other idea, passive beacons. They're way more clever. Instead of making their own light, they just mess with the light from something that's already out there, something incredibly bright. The engineering is, well, it's immense, but the power to actually run it? Almost nothing.
Okay, so if we're gonna build one of these passive beacons, we need the perfect light bulb. And it turns out the universe has one ready-made for us, something called a low-mass X-ray binary, or LMXB for short. Now what is that? Well, picture this. You've got a super dense neutron star. That's the tiny collapsed core left over from a giant star. And it's so massive, it's literally sucking material off a nearby companion star. This cosmic vampirism creates this incredibly stable, unbelievably bright hotspot that blasts out X-rays. It's the perfect natural beacon, just waiting for someone to use it.
And when I say bright, I mean staggering. We're talking more than 100,000 times brighter than our own sun. But here's the truly wild part. All of that energy, all that light is coming from a tiny region, maybe just a few kilometers wide. Let that sink in for a second. That incredible energy density, that's the secret sauce. That's what makes this whole crazy idea even remotely possible. Okay, so we've got our cosmic blowtorch of a light source. Awesome. But now for the million-dollar question. How do you turn that into a focused signal? Well, this is where some really cool physics comes into play. The lens flare mechanism. We're going to use a massive lens, but not to look at something. We're going to use it so that we can be seen.
The basic idea here is actually pretty simple. It's just like a lighthouse or a spotlight. If you put a lens at just the right distance from a light bulb, what we call the focal length, it doesn't magnify it to create an image. Nope. Instead, it grabs all that scattered light and lines it up into a perfectly straight, tight beam. It collimates it. And just like that, you've turned a diffuse glow into a powerful, targeted signal that can travel for incredible distances.
So what would this actually look like to us, trillions of miles away? Well, it's pretty wild. Imagine watching this LMXB. First, as one of these giant lenses starts to pass in front of it, the X-ray signal would suddenly dip. It's being blocked. But then, bam! For just a fraction of a second, when everything lines up perfectly, the lens focuses all that light into a flare thousands of times brighter than the star itself. And then, just as quickly, it passes, and you see another dip before the light goes back to normal. This unique dip-spike-dip signature, there's nothing in nature that does that. It's a dead giveaway.
But it gets even better. It's not just about the brightness changing. It's about what kind of light we're seeing. As that lens transits, the whole spectrum of the X-rays, the mix of different energy levels, it changes in a really specific and complex way. It's not just a flicker. It's like a whole coded message written in the language of physics. This spectral shift is like a second layer of proof that just screams artificial. Seriously, no natural event we know of could possibly fake this. So, okay, the physics works. The signature is undeniable. But what about actually building this thing? This is where we leave the world of elegant physics and enter the realm of just monumental engineering challenges. We are officially in megastructure territory now.
And right away, you hit a huge wall. Problem number one, your lens. You can't just make a giant piece of glass. The high-energy X-rays from our LMXB would just sail right through it like it wasn't even there. So we need a whole different way to focus X-rays. The answer is something called a Fresnel zone plate. Now, instead of bending light with a smooth curve like a normal lens, it uses a pattern of concentric rings, some that block light, some that let it through, to diffract the X-rays and bring them to a focus. It's a clever workaround, but it's got a big flaw, something called chromatic aberration. Basically, it focuses different colors or energies of X-rays at slightly different spots. This smears out the signal a bit. So it's not perfect, but it's an engineering trade-off. It's what might actually be possible.
And it's not just about one lens. To get a signal that's visible all over the galaxy, you need a whole swarm of them. Billions, maybe. And that brings a whole new set of headaches. First, you've got cosmic traffic control. One little fender bender up there could set off a chain reaction, a Kessler syndrome, that destroys the whole thing. So the orbits have to be perfect. Second, that LMXb is so bright, the light itself physically pushes on the lenses. They'd have to be insanely dense, or have heavy ballast just to stay put. And third, a big flat disk just tumbling through space is really unstable. Each one would need some kind of counterbalance, like a long pole, just to keep it pointed the right way.
So, let's say you're a super advanced civilization, and you've solved the optics and you've figured out the orbital mechanics. You're still left with one absolutely mind-bending problem: materials. Where in the universe do you get all the stuff to build this? We're not talking about mining an asteroid here. We're talking about needing a planet's worth of resources.
Let's just try to wrap our heads around the scale here. For just one of these lens structures, say 1,000 kilometers across, and dense enough to not get blown away by the starlight, you're looking at about 310 trillion tons of material. That's like a pretty big asteroid just for one lens.
But remember, one lens just gives you one beam. If you want a lighthouse that flashes in all directions, so anyone, anywhere in the galaxy can see it eventually, you're gonna need billions of these things. Billions of them, all in their own perfect orbits.
And when you do the math, when you add up the mass of billions of these 310 trillion ton lenses, the total weight of the entire swarm comes out to about the mass of the planet Mars. So let's be clear, to build this thing, you don't go mining, you go planet harvesting.
Okay, so you need to dismantle a planet. Which one do you pick? Well, the asteroid belt is out. The materials are all spread out, it's inefficient. But if you were doing this in our solar system, the perfect candidate is right there, Mercury. Why? Well, it's basically a giant concentrated ball of metal. Its gravity is low, so it's way easier to launch all that material into space. And it's right next to the sun, giving you all the solar power you'd ever need to run the operation.
Now, obviously, you're not sending people in spacesuits with pickaxes to do this. A project this big would need a workforce that can build itself. We're talking about an army of autonomous, self-replicating robots. You'd have one swarm that just chews up the planet, another swarm that refines all those raw materials into a usable form, and a third swarm that actually assembles the finished lenses out in space. It's a completely automated, self-sustaining industrial ecosystem. So let's step back. After all of that, solving the optics, the orbits, disassembling a planet with self-replicating robots, you finally built it. You have created the ultimate technosignature. So let's flip the script. What would it take for us to actually find one of these? What does this all mean for our search for intelligence out there?
And this, right here, is why this idea is so incredibly compelling. You know, a typical radio signal we're searching for could be super faint, really easy to miss in all the cosmic static. But this flare, for that split second that it flashes, it could be brighter than all the other X-ray sources in its galaxy combined. This isn't a whisper in the dark, it's a cosmic foghorn.
But of course, there's a catch. There's always a catch. The signal is insanely bright, but it's also incredibly brief and rare. From any one of these systems, you might only get a flash once a decade, maybe even less. And that flash lasts for a fraction of a second. So finding one isn't about having a powerful telescope, it's about having the patience to watch the entire sky all the time, just waiting for that one tiny flicker.
And that really sums it up. The astrophysicist who came up with a lot of this, Brian Lacki, he said it best. The challenge on our end may simply be patience. The technology to see it already exists. The signals could be flashing all around us. We just have to get lucky and be looking in the right direction at the exact right moment. And that leaves us with one last really profound question. Let's say we do it. One day, we see that unmistakable dip, spike, dip signature from a distant star. What does it mean? Are we seeing an invitation from a civilization that's thriving right now? Or are we seeing a tombstone, a colossal monument built by a civilization that vanished millions of years ago? Thinking about this stuff forces us to realize that the search for aliens isn't just about finding someone to talk to. It's about figuring out our own place in the grand, silent history of the universe.